I'd like to welcome you to the 2018 Rutgers CCICADA Colloquium, Data Science, Technology, and the Intelligence Community, an examination of successful strategies. First, I'd like to thank all of the subject matter experts who will share their knowledge and experiences with us today. We appreciate your time and your insights. And many thanks to our partners at CICADA and DIMACS, as well as our student interns for their hard work in making this event happen today. I should also note that today's events were made possible through resources available to Rutgers University through its federal designation as an Intelligence Community Center for Academic Excellence. Since receiving this designation in 2015, Rutgers University has established a popular new minor in critical intelligence studies in collaboration with the School of Arts and Sciences Political Science Department, executed a number of certificate programs in intelligence and national security for undergraduate and graduate students across the university, hosted conferences on the most pressing issues in the field, and developed programs to prepare students for potential careers within the intelligence community. Many thanks to the ICCAE Program Office for its support of our program. Over the course of the day, we will explore how data science and emerging technologies can support the development of actionable intelligence through an examination of successful strategies and case studies. Today's sessions will take place in front of members of the Rutgers community, as well as professionals at the federal, state, and local levels of government and from the private sector, but are also being live streamed to a much broader audience. We hope you find today's colloquium informative and can draw parallels between the lessons learned here today and the research that you conduct or the work that you do at your respective organizations each day. With that, I'm going to turn it over to my colleague, Dennis Egan, who will make a few welcoming remarks on behalf of CICADA and DIMACS.
Thanks, Ava. Good morning, folks. I'd just like to join Ava in welcoming you to the Rutgers University Intelligence Center Community Center of Academic Excellence Colloquium. I'm here representing CICADA and DIMACS centers, which are partnering with the Rutgers Center for Critical Intelligence Studies to bring you this colloquium. The CICADA Center was originally founded as a Department of Homeland Security University Center of Excellence focused on advanced data analysis. Our mission is to provide research and education that applies data science to national security issues. DIMACS, the Center for Discrete Mathematics and Theoretical Computer Science, is really the parent of CICADA. It was founded as a National Science Foundation Science and Technology Center nearly 30 years ago. The mission of DIMACS is to catalyze and conduct research and education in mathematical, computational, and statistical methods, algorithms, modeling, analysis, and applications. Now, we see this partnership between the Center for Critical Intelligence Studies, CICADA, and DIMACS as growing and having a very bright future as the intelligence community and law enforcement agencies increasingly make greater use of data analysis, statistics, and mathematical modeling. In fact, we've been working with Ava and her colleagues on a number of synergistic opportunities involving these centers, and we hope that this colloquium today will present some examples of how data science can be applied successfully to intelligence community issues. I'd like now to turn to introduce my colleague, our first keynote speaker, Dr. Paul Kantor. Paul is Rutgers Distinguished Professor Emeritus of the School of Communication, Information, and Library Studies. He's also the Director of Research for the CICADA Center. And if I brought one item of value to this conference, it is that I've enlisted Paul as our keynote speaker. He is exceptionally well qualified to address us on the topic of data and intelligence. First, he's been the principal investigator and/or technical lead on numerous projects sponsored by the intelligence community agencies. He has assured me that his presentation today has been cleared so that he can share with us at least some of the information on at least some of those projects. And Second, Paul really has a passion for finding out whether a particular new technology or process actually works. Is it effective and useful? And he has many stories, many of them very humorous, about this issue stemming from his work as a consultant to government and other agencies. So I think we're in for a treat, and I'd like to welcome Paul Kantor.
Thank you very much, Ava and Dennis, for inviting me. After an introduction like that, I'm going to be a disappointment. I guess I should say I've got 51 slides here. In my experience, that either means you're in medical school and it's all going to be on the exam, or it's a military briefing and the problem is to keep awake till the end. I also am only allowed to say what's on here. So I welcome questions, but if it looks like I'm checking my notes before I answer, that's the reason. Let's get started. I'm going to talk a little bit about various things that have been called data science, and I stole some very nice slides from a colleague. Then I'll talk a lot about public history. I will talk about activities that have been openly reported. As you all know, there's been a lot of leaked information, and I will not talk about that at all. I'll talk about what analytics can do, really with some emphasis on the limitations that it has. And I'll close with just a few remarks on what to look for if you're shopping for data science tools. Here's an anecdote that I like to tell. Not too long ago, some astronomers had a fantastic idea. They would use a laser to heat up part of the sky to create an artificial light, a kind of an artificial star. And by seeing how much that star twinkled, they would figure out the variations in the atmosphere, and they would use that to remove that variation so they could see the sky better. And they couldn't get funding for it. And eventually they learned that it had been developed much earlier, but was classified. So it had to be unclassified to tell them they couldn't do it. The bottom line is there may be a great deal of wonderful work that we don't know about. It's also true today that there's great work being done commercially, and we may not know how it works. We only get to see the products. People use a gadget called Wordle to see what are people talking about when they talk about data science. And as you can see, they're always talking about data. If you look at data science, you get something like the map on the left, which has the words data science in it. If you look at what's called big data, which is another name for the activity, you see that big and data show up, but the word information shows up. And that's really what the problem is about. There is an awful lot of information, and we need to somehow distill it. Statistics, how many of you took a statistics course once somewhere in your life? Okay. Statistics, in spite of all those formulas, can be a great help in seeing what's going on when it lets you visualize. And this is just the kind of plot you can get when you ask, I've got 4 variables, are they related to each other? And if you look, do I have a cursor here? Is anything a pointer? No, oh, I can turn the TV off. Okay, anyway, the second box in the first row shows you, boy, there's a pretty clear relation, and a statistical formula will find it too. But the third box in the first column also shows a pretty clear relation, and your statistics program is going to tell you there's no correlation between the 2 variables. So statistics is a powerful tool, but it can't do everything. And I think that's true of data science generally. Here's a fantastic example, if you need to fall asleep looking at a picture, showing that visualization can take a huge amount of data and convey it to you in a way that means practically nothing. That's my opinion. That's not an official government opinion. Michael Franklin from the University of Chicago gave a very nice talk about what is data science. And he began by saying, is it really a new discipline, or is it just the overlap of a lot of things? And he had various pictures showing things overlapping. Hacking skills overlapping with subject knowledge and math knowledge, or computer science overlapping with statistics and with a domain. And then he said it's really hard to do it at a university because we have these silos of excellence that don't talk to each other. This is my own picture, so I'll talk about it a little bit more. Over on the left-hand side, we have what you might call original sciences that go back to ancient times: astronomy, chemistry, biology, physics. Over on the right-hand side, we have what you call the sciences, and people joke that if it has the word science in its name, it isn't. That was until computer science put the name in, and then we had to kind of yield. But social science, poli-sci, so forth. These both connect to data sciences. And in addition, mathematics, which is quite old, and statistical science. Statistics is a couple hundred years old, but statistical science seems to have been coined within this, what are we in now? A century, within this century. Anyway, the blue arrow shows what feeds into data science, and all the rest of it is somehow clients for data science. They bring problems, they get solutions, and the interaction between the problems and the methods is the way we move forward. Perhaps we can invent a new one, intelligence science. When you try to read about data science, you feel like you're in a Larson cartoon, which I don't have permission to put on the internet, which says that the dogs don't hear anything except the words that they recognize. And in the same way, if you look at the abstract of a data science paper, you have a hard time picking out what's really going on. This will not be on the exam. I think the point is that the definition of data science and big data is going to keep moving over time, so that it's kind of like the pot of gold at the end of the rainbow. It's an aspiration. But today we want to ask what can be practical. Then I looked around for definitions of the intelligence process. I found a very good example on a DoD site: planning and direction, collection, processing, exploitation, analysis, and production. That's primarily where where data science comes in. Dissemination and integration, and evaluation and feedback. On the CIA Kids Zone, and it's kind of interesting that the CIA has a Kids Zone, there seems to be a shorter one which isn't a closed loop. And I have something that I'm approved to say about that. Let me. I haven't asked anybody about why it doesn't have feedback or evaluation. I know there have been important studies of analytic failure, but on the other hand, CIA have to be very careful not to accept political direction in the disguise of evaluation and feedback. I think that's the point. Okay. Here's a funny personal story. Back in the 1970s, when I was briefly a systems engineer at Case Western Reserve, we had a visitor from Romania who was building a computer system so that the central government could know by midnight where every foreign citizen in Romania was spending the night. I thought that was nutty, but my wife and I encountered something similar when we took our kids, who were very little, on a trip to Bulgaria to study folk dance. And one night we found ourselves staying at a hotel whose innkeeper was illiterate. He didn't want to let us stay because he couldn't fill out the forms that had to be sent every night to the police to report on every foreigner. But fortunately, my wife, who knew Russian and the Bulgarian alphabet, filled out the slips for him. And we got to stay in the worst hotel I've ever been in my life. Okay, times change. Romania and Bulgaria are in NATO. I haven't been there. I don't know if they're still tracking everybody every night. On the other hand, there are reports that the People's Republic of China is trying quite hard to know where everyone is all the time. ODNI ran a competition on visual tracking, and a team from Russia won. We don't know how well US companies are actually doing on it. They're trying to keep low profiles on this for a variety of reasons. Anytime we do things like switching the metro or the subway from tokens to dumb cards to smart cards, we are actually increasing the forensic value of these day-to-day transactions. I've got some sites here to newspaper stuff about China. This is a picture to show that we really did used to do Bulgarian dance. That's at performing when we came back to Ohio. I was younger then. The World Wide Web produces a great deal of optimism. 30 years ago, the idea of automatically processing all the information available to law enforcement and intelligence agencies was really a pipe dream. But search engines have shown us that 10 billion is not an impossibly large number, or even 100 billion things. That is much more than the number of persons in the world, and is getting to be comparable to the number of pieces of information that might be assembled. Now I want to try to take a look under the hood. Some of you may know this already, but I'll say it anyway. How does the internet search really work? Web pages contain a text, and they contain other text called tags, which if you could look under the hood, they're in little angle brackets. And these point to other pages, and they may link to images, to data, and formatting instructions. The secret sauce in dealing with text is that the words are features or characteristics of the page, and that we know how to build an index of words. Why can we do that? It's because we know how to put words in alphabetical order. And once you have things in alphabetical order, you can search really fast in them. So what you do is, for every word, you make a list of all the pages that have that word. There's also an activity that makes use of the links, which is called network analysis or PageRank. It's got some fairly deep mathematics in it, but according to the people I know who are in the industry, it's also got a certain amount of hype. That is, it may not be actually what makes things work. The hope is that the things we're able to do so well will extend in a couple of other directions. And let's see if I have this. Yeah. On the right, we're trying to move out to social networks. That doesn't necessarily mean social media. It could be any kind of connection: familial, financial, co-location-based, organizational. And on the left, we're hoping to move to images. And images can be handwriting, fingerprints, faces, crowds, scenes. The underlying trick in the searching using words is what's called Boolean search. You get some words together. Let's say you want to have word A and word B together. Or maybe you want to have C and D and E, and so forth. There's an unbelievably large number of different possibilities, and fortunately, most of them don't matter. If you talk to people in the intelligence community, they'll say that experienced analysts know what does matter. And over the years, they build up specific libraries. We used to call it the shoebox, where they keep their own secret queries. And the queries will zero in on a specific issue. Typically, they look something like this. I want some word or another word or another word, all of which describe about the same thing. And I want word B or another word for B or another word for C and so forth. And it was said that it's very important, I don't know, I think I could say it anyway. It's very important for a junior analyst who's taking over someone's desk to ask the senior analyst to leave him the shoebox. Modern methods for searching keep track of the Boolean concept, and they may let you actually specify a Boolean combination to search. But when we're searching on the web, it's really a two-step process. There's a Boolean search for documents that contain several of the words you've typed in. And the big companies usually also tweak that by hand. So if I type in hurricane today, not in my notes, how could it have been approved? If I type in hurricane today, I'm going to get links to Hurricane Florence. Okay. And they also use something called vector space concepts to take what might be 1,000 or 100,000 results and rank them. Okay, vectors. How many of you can remember having taken a physics course? Yeah, that's much less. Or a math course with vectors. It's the same people, plus two others. Anyway, when I was a kid, vectors were what you used to push the lawnmower. You only push along the handle. I searched on the internet. I couldn't find a push 'em. There are pictures of people pushing power mowers. A vector has a direction and a magnitude, and the direction could be in real space, like the lawnmower, or in an abstract mathematical space. And the one we use is one where the length of the vector in every direction shows how many times a particular term appears in a document. I have a pilot's license, and so I had to show a couple other vectors. If you take pilot training, you'll learn about lift, weight, thrust, and drag. And if, like me, you have to deal with the FAA for your medical, you learn about dreams, reality, money, and the FAA. Okay, now, if there are going to be hundreds and thousands of dimensions, how on earth can we actually calculate anything about it? It's due to a wonderful fact that you remember from high school geometry. Everybody remembers this, that if you have two lines, two vectors, they determine a plane. So if you have one line that represents your question and another line that represents a document, we can visualize that. It's like this little blue plane here, and there's an angle between them. If we can calculate that angle, we can figure out that the document is close to the query, even if it's much longer because it's got a lot of words. And that's the basic idea. If you had thought of that, you could be a billionaire. Okay. Now, can this really transfer to other domains? To get the same kind of success, we have to find features that are going to play the role that the words do. In handwriting, there are loops and lines, and people try to figure out how the pen is moving in order to get features out of handwriting. For fingerprints, I never saw this word before, so I don't know how to say it. Minutia points. Does anybody know about these? Well, then maybe I'm right. A typical good quality fingerprint image contains between 20 and 70 points that are, in some sense, features of the way it looks. The number depends on the device you've used and how the person puts a finger on there. The system stores that information along with demographic information. So that's how it's possible to search in fingerprints. For faces, there are maybe 40 to 80 specific features, and they're all numbers. Just a second. Let's see what I can say here. Nothing more. Just a second. Now, that's it. I can say that I know something about this. The way that processing handwriting works, it's actually used by the post office to read what you scrawl in the envelope. And the point is they've gotten very good at reading the last 5 numbers, the zip code. And then all they have to do is figure out whether what you wrote corresponds to a name of a street that's in that zip code. And that's why they want us all to use more. Okay, so we're back here looking at all these things. And here's some, you may have heard this word, wavelets. Wavelets are a completely different way of looking at images. It doesn't look for specific little features that are in there, but looks for overall patterns. For example, the picture on the left doesn't have an overall pattern. It's easy for us to see what's going on. It's a picture of someone thinking hard about chess. The picture on the right is a perfect example of something that has a very regular overall pattern. What wavelets do is they take a picture and they divide it into successively smaller pieces, and they try to figure out when patterns emerge. Now I'm going to talk about some of the ways you can find out about new things or things that are in development. National Institute of Science and Technology stood up something that has now become the Information Access Division, and they are the go-to group for evaluation of many computer programs that develop data science to support intelligence. They've been running something called the Text Retrieval Conference since 1991, before the World Wide Web, because the search engines that we use today have evolved from very clever efforts to replace the library card catalog with a computer system. And those things were being developed during the 80s. They run other conferences on message understanding and on summarization. And a lot of them were initially funded by a DARPA program called Tipster. There are other competitions outside of NIST. DARPA really initiated self-driving vehicle competition by asking whether somebody could make a car without a driver that could drive in the Mojave Desert. And according to it's not in my notes, according to who sent the latest press report to the newspapers, that was either invented at Carnegie Mellon or at Stanford. But the fellow who was working at Stanford, Sebastian Thrun, went to Google, and they seem to have moved very, very quickly. The Tipster program drove many of the developments in document retrieval. Amit Singhal figured out an even better way of controlling for documents that are too long, and he's retired now from Google, where he was chief of search. Steve Robertson was the guy who developed the first retrieval system for card catalogs, and he moved from University College to Microsoft, and there's just many, many others. Not all the work has been evaluated by NIST. Some has been done by the Office of the Director of National Intelligence. There was something called the ARDA program, Advanced Research Development Activity, I think. They did a question answering challenge. ARDA has evolved into IARPA, which is the intelligence agency's DARPA. And now I've got the eye chart. Is that too small to read? It's fine. Okay, good. Then I won't read it to you. I didn't intend to. But I've sort of bolded up various programs, and you see words like natural language processing, image processing, social network analysis crop up over and over again. Notice down at the bottom, sociology of groups. They're really trying to support research that not only does mathematical computation, but makes use of what we know about how people behave. Here are some current programs, and I didn't bold any of the letters. We see machine learning a lot more, computer vision, something called natural language processing. This is the ongoing effort to enable computers to have some sense of what a text means. I want to go back now and look again at that picture of me and my wife when we were much younger dancing. If you look very closely, you can see in that picture a reflected image of me taking that picture with my cell phone. My large right ear is right over here. Okay? Now, that's exactly the kind of thing that we would really like to be able to dig out for forensic purposes. And it's hard to do. It's not part of this high volume problem, how do we keep from drowning? It's another kind of looking at data, which is what people do. My phone, when I went to take a picture of this picture, which hangs on a wall, quickly identified that there were two people there. It actually put this little box up. So that's become cheap and easily commercial. But it didn't notice the side of my head and my ear. Okay, what do people do with faces once they've seen them? Alex Pentland, quite a while ago, came up with the idea called eigenfaces. An eigenface is an eigenvector, remember vectors, for some operator that represents facial shapes, and they wrote a lot of papers about it, and they got patents, which I suppose expired by now. It's more than 20 years since this, and there are other ways now, primarily and somewhat alarmingly, something called deep neural nets. These are intended to mimic the way the neurons in our brains work. Of course, we don't understand how our brains work, and the result is we also don't understand how deep neural networks work. This is a meaningless picture about the Society for Neuroscience. Okay, here's a simplified picture of a deep neural net. It's got a lot of things that are sort of the imaginary neurons, these little circles, and they're all connected together, and they're in layers, and they're all connected. Let me see what else I can say about it. Sorry. Okay, something comes in on the left-hand side, let's say an image, and what comes out on the right-hand side is a label. And the way these things work is that they're connected by connections with variable shape and strength. And during a process called training, hundreds of thousands or millions of images are fed to this thing. And when it happens to get it right, it sends a message step back saying, okay, the way the signal came through was a good one, make it stronger. When it gets it wrong, it slaps it upside the head and says, weaken those connections. Okay, as soon as you have something that appears to work like magic and better than you would expect, people say, well, how good is it really? And there's very interesting work now on what are called adversarial images. People have been able to show that given a particular deep neural net, which is in a box now and it's going to recognize things, we can give it pictures that it gets ridiculously wrong. And I have to thank a postdoc at Wisconsin for these slides. Here's a picture. How many think it's a panda? Others are not willing to commit themselves. Okay, the system says with 57.7, I love that 0.7% confidence, this is a panda. These guys then added 7/1,000ths intensity of a picture which looks like those dots, which, by the way, the classifier understood that it didn't understand. It thought it was some kind of a worm, but with only 8% confidence. When you add them together, it looks at that new picture, and you can see the new picture on the right, and says, that's a gibbon. And I have 99.3% confidence. Okay, clearly wrong. That's what gibbons look like. Here's another example. This is the already fooled with picture, but it looks to me like a couple guys standing in the snow, probably in the mountains. The system says with 91% confidence it's a dog, with 87% confidence it's a dog-like mammal. The first thing it has right at all is that there's snow in the picture. Here's another one. We often have to deal with other languages, increasingly now. Does machine translation know what it's doing? So I tried Google Translate. I will say it used to be possible to give it English, translate it to German, and then give it to German and get back different English. But the folks at Google figured that out, and so they save everything they've said to you, and if you give them back the right-hand side, they give you the one you put in. So I made little loops. I typed, he did not mean to imply that the cat stole the automobile. A witness might have said that. I took it from English to Bulgarian. It came back fine. I took it from there to Hungarian. It came back fine to English. Then I took it into Basque, which is a very unique language, and back to English. And at that point, the output was, I do not really think the car that stole cats. So where do we stand today? Algorithms are impressive. They're not perfect. They can reduce workloads. It's always a balance between missing something and running over your budget. There's interest, and if you've been following the news from the UK about the guys who are believed to have poisoned the Skripals, the UK used image processing, but they also used people that they call super recognizers, who are just much better than most of us at recognizing people. We still have to worry about adversarial images. Voice recognition has gotten quite good in the sense that it knows what I'm saying or what you're saying to your phone. Whether it can tell that it's you or me, I'm not so sure about. By the way, my phone isn't really that smart. After I sent 3 emails to a government point of contact named Shawn, S-H-A-W-N, it didn't recognize when I wanted to send something to my son's brother-in-law, who's also named Shawn. Why did I put this? I wanted to show off my ability to do a paper chase and dig up something nobody knows. There's a phrase you may have heard in English before, kill them all and God will sort them out. there's something strange about neural nets because the way they process it is they say, okay, we're going to let every pixel in the image come in and be processed. And somehow the neural net is going to sort it out and figure out which ones should count. The path forward. It's always hope versus hype. For individual data centers and intelligence centers and fusion centers, it's really hope versus hype versus budget realities versus privacy concerns, and we'll have a talk today about that. It is really, really important to get it right. No one has beaten what Condoleezza Rice said in testimony about 9/11. The terrorists only have to be right once. We have to be right 100% of the time. It is really, really hard to be right. Next generation identification of fingerprints is facing a problem of needing a system that could be as good as 1 in 10 billion errors. And at a rate of, and when you combine the whole processing, that results in about 1% wrong. And they do 150,000 a day. 1% of that is 1,500 wrong identifications. I wanted to show a slide. How am I doing on time? But I don't know, when do I have to be done? Okay, I can slow down. It'll be all right. I don't know how big the intelligence community's budget is, but in 2019, for 2019, I found a request of, I guess, 60 billion. The Google parent company, Alphabet, has an annual revenue of 110 billion. So industry has hugely more money to throw at these things than the government does. Right now, DARPA has a program that they call Modeling Adversarial Activity. They give a gigantic network of transactional data, kind of an extended social network, and the challenge is find what's going on, find who's connected to whom. Meanwhile, the team at Facebook have already scaled up the technology, which is called graph search, to billions of edges and nodes. Where can we expect innovation to come from? A lot of it is, in fact, coming from small companies, which generally then get bought by bigger ones. It comes from clever people at big companies. It comes from clever people at universities and colleges who increasingly are being hired away by big companies. And it comes from clever people in government who then leave government and start a small company and get bought by a bigger one. Companies and contractors are very valuable in this process. They're agile, and the competitive market does very good natural selection of killing dead ends. Right now, and it's more today than when I prepared these slides, private companies are becoming very skittish about being known to have ties to the government. They are concerned about their international markets and that our government might be doing the same thing that we're sure the governments of China and Russia are doing. I didn't check. Okay. There's increasingly also a problem for decision makers. You don't want to use a tool if you don't know how it works. In the old days, we knew the general outlines of how the technology works. That very first few slides I showed you. There were students or engineering personnel who keep making adjustments to it The bottom line was that no one person really knew exactly how it worked, but at least we knew that people together did. In the new way, we know the general outlines, machine learning, random forests, deep neural nets. They make millions of small adjustments, and they cannot explain it to us. The bottom line is that none of us really know exactly how it works. When I was doing the research to prepare these slides, I came across an interesting fact. There's a paper that reports that if you're training neural networks, randomly giving them misinformation may actually help them to learn even faster than telling them the truth. I have no idea what that means. Why does all this matter? You know, we don't know, most of us, how the airplane flies, but we still travel. But there are some serious problems with not knowing how the stuff works. One of them is baked-in biases, prejudice, and frank injustice. For example, with a monetary bail system, poor people who have been accused are much more likely to sit in jail. Ellie, where are you? Pardon? Oh, Ellie isn't here yet. One of our later speakers actually was involved in the breakthrough that's been made in New Jersey to get rid of that. But the problem is, if you hand data about this to a machine learning program, it's going to say, hey, poor, put them in jail. The other problem is adversarial exploits, these things I showed you that can produce huge misclassifications. You know, imagine trying to go into court to make a case and you say, here's the magic software we use to identify this guy. And the defense says, okay, here's a picture of two skiers. Let's see what your software says about it. Oh, it's I forget what it was now, a dog? Dog-like mammal, okay? So what can data science do? Data science can discover an association between two different things, even across time. It can discover that some behaviors are associated with others. It can discover that some patterns of personal history associate with future behavior. All of this is discovery. Data science can also find likely candidates in thousands or millions of fingerprints or license plates or social media posts. All of this could be called distillation. I like to put this together in an Escher mind-boggling triangle. What it cannot do is that third leg of making a decision. Data science cannot issue a warrant, impound a vehicle, bomb a hideout, and so forth. When we find data science in use, it's generally working with humans, the human in the loop, and the algorithm is supposed to do the tedious parts. It's a kind of intelligent assistant. There we go. If you have the option to invest your organization's money in data science, here are some tips I would give. Formulate very clearly the question that you want the algorithms to answer. Then make it simpler. Keep doing it. Keep doing that until you get to the point where a machine can do it. For example, does this license plate number appear in the list of stolen vehicles? Examine your own work processes to identify things that are important to do that could be done by a really, really stupid human being. And then look for an algorithm that already knows how to do that. Beware the vendor who says, our algorithm is so hugely general that it can solve your problem, and we will have to work closely with you to iron out the details, because behind that Valentine, the truth is, till death do us part. Thank you, Ava and Dennis. Thanks to my supporting agencies. Thanks to Rutgers School of Communication for accommodating my interest in this when they thought that we were there to teach librarians. and to many colleagues at CICADA, DIMACS, Library and Information Science, Computer Science, Operations Research, and the Department of, that's my mistake, Industrial and Systems Engineering at the University of Wisconsin. Do we have time for some questions? Okay. Thank you very much. Sure.
Well, I have an extraneous question. Why is the rectangle on the faces of the golden rectangle?
You mean, why is it gold, or why did?
You meant that it had the ratio of the sides. What am I? The golden, is that the rectangle golden?
Oh, it can be different colors on different phones.
Okay.
It's just to show that it spotted the.
Sorry. I thought you were referring to the shape of the rectangle.
This is allergy heaven. I know what you mean. No, it's not the golden ratio.
The golden ratio, that's
Yeah.
what I had heard you say.
Any other questions? Going once?
Okay, so now I have a real question.
All right.
You had the slide about science, and then the things that aren't real sciences. but
Oh, yeah.
sciences.
Yeah, let me see if I could.
So one of the things I get to deal with is materials science, as opposed to social science.
Materials science.
But you make no mention of the engineering disciplines on that.
I'm going to get dinged for that.
You just did. Right.
I just wanted to stick with the word science. Some parts of engineering now have the word science in their name, others don't, because engineering is a perfectly good term. When Google hires people, even though they hire people who get degrees in computer science, they hire them as engineers. Because what they really want, I mean, the implication of engineer is you build something and it works. Whereas in science, there's somehow the notion that you're looking for the abstract principles that will be used by other clever people to build something that works. It's a fair question. So I got 2 mistakes in the slides so far. Fred, if it's a third, I don't want to hear.
No other mistakes, and I'm good at finding them. I have a little quibble with saying that maybe machines can't make decisions. Or shouldn't make decisions.
I'm saying shouldn't, and I'll fight with you, you know.
Let's take, for instance, the smart grid, the power grid.
The power grid, yeah.
And we're in the old days, every 10 seconds we would get an update on the status of the power grid, lots of data. Now we get an update 10 times a second.
Yeah, I'm gonna jump ahead and yield the point to you. Because Fred's talking about the stability of the power grid, but there's actually a better example. If you get to fly on a big airplane, in fact, there is software in that airplane that is making second by second or millisecond by millisecond decisions about the control surfaces so that you have a really smooth ride. So there are decisions, sort of operational decisions that we have already entrusted to machines. And in fact, I've read, although I've never tried it, that high-performance aircraft, high-performance military aircraft can barely be flown by a human being if you were to cut off those internal control systems. One more question? We'll call those the little decisions.
You had mentioned a Russian company that won the bid for,
Not won the bid, won the
or
competition.
won the competition for the China's seeking?
No, it was a U.S. competition sponsored by our ODNI.
Okay. Are you worried at all? You also had mentioned the reluctance of American industry and companies, especially big ones, to relate to the government. Are you worried in terms of the U.S. security long-term with that reluctance and potentially other countries without that reluctance in terms of security in general?
Is the camera still on? Pardon? Yeah, let's turn it off. Is it off?